Okay, guys, it's Tuesday, so working on that homework that I assigned you guys for tonight. If you need a little bit of help, just move to whatever problem it is that you're interested in. I will start with number 2 and just work through these evens. So a rancher wants to construct 2 identical rectangular corrals using 500 feet of fencing. The rancher decides to build the adjacent, make them adjacent to each other so they are share fencing on one side. What dimensions should the rancher use to construct each corral so that together they will enclose the largest possible area? That is a big statement right there. Largest possible area tells me I want to maximize my area. If I'm maximizing, maximization comes from first derivatives, doesn't it? So I want to take my first derivative, set it equal to 0, and find out these critical points. So we've got 2 corrals sharing one side. They're going to be identical sizes. So we can let, if you want, you can go x, x, x. That's the width of my corral there. And then I'm just going to say this combined is all one length y. I should be able to write 2 statements from this. The obvious one is about the perimeter. I could say 500 feet of fencing is equal to 3x's plus 2y's. That's the distance around there. On my other statement, I can say that the area of my pens, length times width, or x times y. I know I want to do a derivative on area. If I do it as it's looking right now with xy, I'm going to have to do implicit differentiation. And I can get around implicit if I go back to my perimeter statement, solve one of these out for x or y. I think I'll solve for y. So I'm going to go 500 minus 3x is equal to 2y, and then take half of this and get down to just y. So 500 minus 3x divided by 2 is my y value. So now over on my area statement here, I'm going to update that and change this up so that I have area is equal to x times, instead of y, we're going to put the 500 minus 3x divided by 2. Now you'll notice we have a function that's in terms of x's. So let's take and I suppose distribute, or we could even simplify. I'm going to say area is equal to x. 500 divided by 2 is 250. 3 divided by 2 is 1.5x. How about that? And that means area is equal to 250x. I'm going to try and get around the product rule here by distributing through, and a 1.5x squared. Nice. Now let's do first derivative. First derivative would make this 250 is equal to 3x. Maximize that baby. So 0 is equal to, whoops, this should be minus. 250 minus 3x. 3x is equal to 250. Divide by 3. 250 over 3 is my x value. So you could check, definitely, probably should, at 250 thirds, do I have maximization occurring? What I'm looking at is, okay, on that first derivative, am I moving from a positive first derivative to a negative, where I'm increasing, decreasing on my sign chart? And indeed we are. So x, we want the distance this way, x across the pen is equal to 250 thirds. Figure out what y is, plug this into that, and you'll get your y value. Go ahead and solve that out. Next, let's move down and see problem number 4, I guess it is. I'm going to hit my screen and clear that. Number 4. They want us to do a left-hand Riemann sum. I'm just moving that over so that it's out of my way and I have a little more room. They did not state how many intervals, so I'm just going to assume we're going to pass through and do, looks like 4 intervals. Notice that delta x continually changes on each of these intervals. So I can't really take a lot of shortcuts methods on this. And we want left Riemann sum. So what are you doing when you're doing a Riemann sum? Well, you're building rectangles, right? We're estimating the area under the curve by building rectangles, all based on the height from the left-hand side. That's the main idea. The distance across the bottom is my delta x, and my change in x, and the height is f of x. Well, f of x represents y, doesn't it? And there is our height in terms of y, but using the variable x. Let's go through. I know there are 4 rectangles, so my area, simply put, is going to be the width of this, which is a 3, and the height, based on the left-hand side, is 4. So I'm going to have 3 times 4 for area number 1. Area number 2 is rectangle number 2, and that moves from 3 to 4. Distance from 3 to 4 is a 1, so that's the change in x. The height, based on left-hand side, is a 3. Moving on to rectangle number 3. I am going to look at distance from 4 to 8. That has a distance of 4 for the width, multiplied by the height. Left-hand method would be 2. Added with 8 to 10 is delta x of 2 times left-hand height. Right there, it's 3 tall. Now, I think you guys can handle the math from here. See what you come out with. Backside, let's look at number 6. This particular problem says, for each problem, approximate the area under the curve over the given interval using 4 midpoint rectangles. Okay, 4 midpoints. And I'm on an interval from 1 to 5. So my delta x are all going to be the same. I can use the ending position minus the beginning x value divided up by 4 intervals. Well, that's 4 divided by 4. It appears that delta x is going to be a distance of 1. So every rectangle that sits under this curve is identical in its spacing. Each one is a 1. Delta x equals 1 on all 4 of these. Midpoint wise, okay, this will be interesting. I think I'm going to do a chart. Just trying to think of the best way to lay this out for you. So this is value at 1, 2, 3, 4, and 5. My midpoint between 1 and 2, you know what, I'm going to back up again. Let's go with interval between 1 and 2. This will look better one at 2 and 3, 3 and 4, and 4 to 5. All have delta x of 1. So delta x is 1, 1, 1, and 1 widthwise. Next, let's talk about the midpoint in this. The midpoint x value, that would be at 1.5, 2.5, 3.5, 4.5. Next thing I need to know then is what is the height at each one of those. So the height of my rectangle. Take 1.5 and put it into the function, and it says y is equal to 1.5 plus 3. That gives me 4.5, doesn't it? 2.5 plus 3 gives me 5.5. 3.5 plus 3 gives me 6.5. 4.5 plus 3 gives me 7.5. Those are the heights. Now I can get my area, and I'm sorry, I'm running into the next problem. Area. Area is simply length times width. So I want to calculate width times height. Width times height. Width times height. Width times height. Well, 1 times itself is going to be itself, or times anything. How about a marker color? So I'm going to have 1 times 4.5 gives me 4.5. Added with. 1 times 5.5 is 5.5. Added with. Area of 6.5 times 1 is 6.5. Added with 7.5. You add them up, and you're going to have unit squared for label. Number 8. For each problem, determine if Rolle's theorem can be applied, and if it can, find all values that satisfy C. So for number 8, Rolle's theorem, just a quick background on Rolle's theorem. We'll do it over here under number 9. Rolle's theorem has a couple things that has to happen on it. Mainly one, it has to be a continuous function. Next thing is the height at one endpoint has to equal the height on the other endpoints. And notice I'm writing them in function notation because that really means y is equal to y here, right? Y evaluated at A and y evaluated at B. Those heights have to be the same functions. Functions evaluate at some value. Okay, I know that, well, I don't know that this is continuous, but on the grounds from -6 to 2, this function, I think, would appear continuous. It has a domain issue at x equals -7, but since that is not in my interval, I'm going to state that this function then is continuous. So I can continue with Rolle's theorem. Now I want to check out my two endpoints, f of -6, f of 2. Excuse me. Okay, f of -6, plugging that in, I do believe you'll find that turns out to be 0. F of 2, you'll also find out that equals 0. Thus, my conclusion is that f of -6 indeed is the same height as f of 2. Their y values agree. That means, remember when we did this in class for notes, I had you plot some point A we called it, and we plotted some point B exactly at the same height. Join them up with a secant line. Their secant line is basically the average slope between the lines, and that has a slope of 0. What Rolle's theorem assures you is that if there's a continuous function passing through A and also through B, somewhere along this path, in between little a and little b, x values, there has to be a point that the slope, or the first derivative, is equal to the slope between points A and B, which was a slope of 0. So it assures it that there is some point that that's happening. And I'm going to dot that down. That would be some value C down here where x is equal to C. That's what they want us to find, is that point C where this occurs. So what I want to do is take my first derivative of x and set it equal to 0 and find C. I guess I could say f prime of C is equal to 0. Okay, first derivative. You get to do the quotient rule. Fantastic. So quotient rule says low d high minus high d low. Low d high. And then that's not what I wrote, was it? Derivative of the top is 2x plus 4 minus high times derivative of the low, which is just a 1, all over low squared. Okay, and then do a little bit of work on that, and it simplifies out into an x plus 10 multiplied by an x plus 4 all over an x plus 7 quantity squared. There's our first derivative. Set it equal to 0. Not going to worry about the bottom going to 0. I'm going to look at x equals -10, x equals -4. But remember, we were on restrictions up here. Our interval only went from -6 to +2. It appears that our C value that we're interested in stating is C equals -4 is where there would be a slope of 0. Good enough. That's what I had for you today. Hope that refreshes you on some of the things that we've been doing.